Hey everyone, continuing with chapter 13.3 notes. This is Hamiltonian circuits and the traveling salesman problem. This is a little bit lengthier, so I had to split it up and split all of these into separate videos, but regardless, here we go. So we talked about Euler circuits and Euler paths, so we might as well talk about Hamiltonian circuits and Hamiltonian paths, which is just a different kind of path/circuit. A Hamiltonian path is one that uses all of the vertices in the graph exactly one time. So instead of using all the edges, it uses all the vertices. It still uses edges, it just passes through each each vertex one time. Most Euler paths repeat vertices, so they definitely don't count as Hamiltonian paths. And a Hamiltonian path almost always doesn't use all the edges. There are exceptions, but they're pretty rare. So the point is that they're not going to be Euler paths. These are distinct things. There's not actually an easy way to determine if a graph has a Hamiltonian path. It's actually one of those problems in mathematics that people spend a lot of time working on. And we don't have a really nice answer for how to figure that out. Now that doesn't mean it's impossible. In fact, for small graphs, we can just use trial and error to find out if a graph has a Hamiltonian circuit. And we can take an example for the graph on the left. And there's a pretty obvious one, which just is the exterior of the shape. So if you just trace it in the shape of a hexagon, you get the thing. And that definitely has a Hamiltonian circuit. It doesn't have an Euler circuit, though. It actually has four vertices of degree 3, which is kind of a problem. And then the right graph, however, it doesn't have a Hamiltonian circuit. And this one is a little trickier to see, but if you mess around with it a little bit, and I recommend messing around with it a little bit with a piece of paper, well, any attempt to add a circuit, you're going to have a problem with that weird degree 4 vertex, because, well, if you start on the top part, then when you can't get back, and if you start on the bottom part, you can't get back. But if you start at that point, then you're going to cut off an entire section. Like that central point is kind of the problem. However, it does have an Euler circuit, so there's not even an difference between those things. Like they're just because it has one, it doesn't have to have the other, and vice versa. So with that, we can move on to. Now, just because there's no easy trick to find a Hamiltonian circuit in some random graph, and it can be kind of time-consuming, especially for some really big ones, this isn't the case for what's called a complete graph. A complete graph is just a graph where every vertex is adjacent, or, they share an edge with, every other vertex. So this blue graph, for example, is a complete graph, because you'll notice that every vertex is, sharing an edge with every other vertex. And a complete graph with at least 3 vertices is guaranteed to have at least one Hamiltonian circuit. If you have 1, then you don't have any edges. If you have 2, then you're just a line segment. But 3 is a triangle, and that a triangle is definitely, a Hamiltonian circuit. Here is a good question, is rather than just saying, well, I know there's 1, how many are there? Well, the graph on the right, it's a complete graph, so again, guaranteed one Hamiltonian circuit. But the real question is, how many can I reasonably make? And by reasonably, I mean how many can I make? So I could form the ABCDA, that's the rectangle shape. That's pretty reasonable. And every vertex is actually adjacent to every other vertex because that's the whole point of a complete graph. Well, I could just write the names of the vertices in any order I wanted, and then just repeat the first one, and that's a Hamiltonian circuit. So if you say like BDCAB, well, doesn't even matter. You don't even need to draw it out. Guaranteed to exist, and guaranteed to use each vertice one time. That's great. But the problem is that A, B, C, D, A, well that's the rectangle. Well, so is B, C, D, A, B. You start at the top right, and well, it's the same thing. I just started at this different point. It's still the same rectangle. And, well, I could also go backwards. So A, B, C, D, A is just A, D, C, B, A. Like, it just one's going clockwise and the other one's going counterclockwise. That's kind of annoying. So we can then ask the question, how many Hamiltonian circuits are there? Because we know that a complete graph has to have at least one, but how many does it have? So here's our basic example from before. There's actually only 3 of them. So we'll look at the first one. It looks like this. It's A, B, C, D, A. There's several other ways to write it, but we're going to write it that way. The next one looks like this, which you can tell is a different shape, so we know it's a different circuit. And that's A, B, D, C, A. And then the last one, it's the sideways hourglass kind of thing. Well, that's A, C, B, D, A. And if you want, mess around with it a bit. Make sure that I'm not lying and that there's no other ways to form a Hamiltonian circuit. Because again, we don't really care about who started because it's all just one big loop. And we don't care the direction for the exact same reason. But the problem is if I was to give you a more complicated complete graph, one with more vertices, well, then this becomes completely impractical. And instead, we really just want to know the number, so we can use a formula where n is the number of vertices. And that is the number of unique Hamiltonian circuits, or cycles, that's another word for it, is n minus 1 factorial over 2. Let's look at that formula again. N minus 1 factorial over 2. And yes, the exclamation mark, it just means factorial. That's how you say it. And all that means is you take the number you put in, you multiply it by 1 less than that, and then 1 less than that, and then 1 less than that, so on and so forth until you get to, 3, 2, 1, and then you're done. So for this graph, it's got 6 vertices. Well, 6 minus 1 is 5. So that's 5 factorial over 2 circuits. Well, if I do that, I'll get 5 times 4 times 3 times 2 times 1. That's 120. All over 2. That's 60 different Hamiltonian circuits. And that and by the way, when I say 60 different ones, that means 60 unique shapes I can make that touch all 6 points. So let's apply this with something called the traveling salesman problem. So one of the biggest applications of graph theory is actually just the traveling salesman problem. It's one of the most famous problems that you can have in the graph theory space. And the problem involves adding weights to each edge. This is just going to be a value we're going to add to each edge on the graph, like so. And any path on the graph is going to be given a score, and that's just the sum of all of the edges in the path. So in this case, A, B, C, D, A has a score of 12 plus 17 plus 19 plus 8, which is 56. And again, the circuit we've made is, well, that's just the exterior square. So now that we know that we can talk about the total score, we can say that the traveling salesman problem is actually about finding the Hamiltonian circuit with the lowest possible weight. So in this case, we might talk about what is the best possible score for all of these. So a practical example that this is why it's called the traveling salesman problem is that you think of every vertex as a city, and the edges is just the distance between each city. So if A is New York and B is Atlanta, then 12 would represent the distance between them. So I don't know what that would be, 12 whatever, but it doesn't really matter because this is an abstract example. Either way, then you can ask the question, like, what's the shortest amount of travel time? Because if if you're a traveling salesman, you kind of have to end where you started because you live where you started. You've got to go to all the cities, and your goal is to minimize the amount of time you actually spend traveling. So this has real applications, often with delivery. So if you're like the Postal Service or Amazon, then this is a very simple kind of question that they might ask. But they usually have more than 4 cities. And one way to solve this problem, like just flat out solve it, is to just check all of the possible circuits. And this is known as the brute force method. So A, B, C, D, A, like that was our outer square that has weight 56. A, B, D, C, A, well that's got weight 49. And A, C, B, D, A, that's got weight 43. And feel free to check. Again, you just have to add up the relevant edges and you should get a number, and you're either going to get 56, 49, or 43, depending on which Hamiltonian circuit you picked. There's only 3. You got the square, the bow tie, and the hourglass. Now, this is guaranteed, this strategy, the brute force method, it's guaranteed to get the absolute best answer. But it's also really terrible for anything that's remotely large. So like, let's say you had 20 vertices, there are 60 quadrillion Hamiltonian circuits. And that, well, I can't check all those, even with a supercomputer. And the bigger problem is, again, if you're Amazon or the Postal Service, you have more than 20, you have several hundred. And this is not feasible. So instead, we have to pick answers that might not actually be the best, but relatively good. So the tactics from here on out that aren't brute force aren't going to necessarily get you the best answer, but they will get you an answer that's usually pretty good. And the key thing that we like about them is that they're faster. The simplest one to kind of understand, at least I think, is the nearest neighbor method. It's pretty straightforward. All you do is you start at any vertex you want, doesn't matter. Go to the nearest neighbor that's unvisited. So think of all the vertices you haven't gone to, and then go to the one that has the edge would be the smallest. And then repeat this process. Keep doing it till you get all the things. And that's it. That's the whole algorithm. So let's apply it to our previous example. So we're going to pick a random vertex. I'm going to pick B, but you could have easily done this with a different vertex. And we're going to get to that in a minute. But for now, we're picking B. And B, well, from B, there are 3 edges connected to B. One has weight 12, one has weight 13, and one has weight 17. Well, 12 is the smallest, so let's pick that edge. So we made the top little line. We're now at A. Well, we can go 5 or 8. 5 is down and to the right, and 8 is down. We can't go back to 12 because we already went to B. So we're going to go to 5 because that's the cheapest, so we're going to C. Okay, so now it might seem like, well, we can get back to B because B is technically the cheapest edge we see, but then we've already used vertex B. We're not allowed to go back there because this is a Hamiltonian circuit. So we're forced to go to 19. And there we go. And we're not done. We have to finish the circuit. So at vertex D, well, we have to go back to B for 13 because we have to finish the circuit. So therefore, the nearest neighbor algorithm, it's going to give us the circuit BACDA. And sure, you could start it at A, but ultimately it's the same kind of idea. We make this hourglass shape, and it gets us a score of 49. And that's it. So before we start celebrating with our cool result of 49, that wasn't actually the best route. the best route was actually 43. This is the example we did the brute force on, so if you go back, you can check. But had we started with A or C or D, we would have gotten a better score. So it turns out the vertex you pick at the beginning does have an effect, but you can't tell until you check everything. Well, why not check everything? So we have a slightly more tedious algorithm. It's known as the repeated nearest neighbor algorithm, where you repeat the nearest neighbor algorithm for every vertex. Then you pick the best answer, and you're done. So in this case, it turns out that picking A or C or D would have gotten you a score of 43, which was the optimal score we checked. So repeated nearest neighbor algorithm gets you the best possible answer. Not always, it just happened to work in this case. This is not guaranteed by any means. But the problem is that the guaranteed method is to check every single circuit. And if there were like 50 points, that number's way too big. But I can check 50 times. I just can't check, 49 factorial over 2 times. It's way too many. You might notice that there's a lot of edges in a complete graph, like a lot. And so when we want to draw a complete graph with 4 vertices, that's fine. 6 is doable, but oftentimes when it's even remotely large, well, we're just going to represent the graph with a table. Table looks like this, by the way. It's relatively straightforward, but it might be a little bit weird if you've never seen something like this before. This actually represents a complete graph with 6 vertices. You can tell because it has 6 rows and 6 columns. And all of the numbers are weights on all of the edges. And that's what the graph actually looks like, and you can see why I wouldn't want to put all of those numbers in that graph. It would take up so much space, it would be ridiculous. So to find the value of an edge weight, all you do is you find its section in the table. So we could look at, say, BC. See that top right kind of edge there, where we go to row B and column C. Well, in row B, column C, that's 5. So that means BC has a weight of 5, and you can put a little 5 there. I'm not doing that for all the values, but that is the case. Now, the key thing here is that this table is designed so I don't have to write all of the stuff. And in fact, oftentimes it's the only reasonable way, and you're just going to be giving this to a computer in most real-life examples. Now, before we start applying that, we're going to start talking about the sorted edges algorithm so that we have a good application. So this is another strategy to solve the traveling salesman problem. Again, it's not perfect, but the best part is that you don't actually have to pick a starting point, like at all. It's not required. Instead, we'll create a Hamiltonian circuit by just choosing the edges, but in more of a big picture kind of way. So all we do is start with the lowest weight edge in the graph, and we're going to add it to our little circuit. Then we're going to pick the lowest weight edge that wasn't used, and we're going to add it, and just like before, we have a catch, unless adding the new edge gets a circuit that's too small, which would make this impossible, or adding the new edge would cause a vertex to have degree 3. And then we keep repeating step 2 until we have a circuit. And that's it. So let's finish this off with one more example by asking how this works in practice. So let's look at this graph. And by graph, I mean this table, which represents a graph. And this is going to be the end circuit, the end result here. Oh, I'm not going to draw any edges that are not relevant. So if you look at the table, the smallest number in the table is 3, and that's AD or DA. It doesn't matter. They're mirror copies of each other. In fact, you can just think of the whole thing as the top right triangle or the bottom left triangle, one or the other would be fine. You wouldn't lose anything. And then we're going to add that AD. Next cheapest, that's BC. BC has a score of 5. It's the second smallest. So let's add it to the graph. Be aware that I didn't have to connect it to the first edge. There's nothing requiring that in this method. So then I can add BD, which is 6, and then AE, which is 7. And we're basically done, except we have to address this F thing now. But we're not thinking that way. So the next cheapest thing is an AB, which is 8. AB has a score of 8. But I can't pick that, because if you notice, if I was to draw AB, well, then there would be 3 things coming out of A and 3 things coming out of B, and you can't have a degree 3 thing. That's one of the rules against this. So then we say, well, what about CE? That's next up. That's 9. Well, CE is also impossible, because what would happen is I would close the circuit, and I would close the circuit early. So actually, my options are incredibly limited. So instead, I have to go all the way to CF, which has a score of 23, and end with EF, which has a score of 45. And that's the circuit. This isn't necessarily the best circuit, but checking all 60 combinations is not reasonable. And so we don't. In real life, checking just 6 vertice complete graphs for the best version is fine because we have supercomputers. You don't need a supercomputer to solve that problem, but supercomputers exist. And so the problem is more along the lines of, once again, there are 100 cities, and how do I solve that? So that's the end of these notes. Again, normally I would have a little end thing, but I still have 13.4 coming along the way. If you have questions about this, you can email me, you can send me a message through Canvas, you can come to my office hours, all of the same stuff. It's still just as true as it was when I made the previous video, and when I make the rest of this course, it'll still be that way. If I can help explain any particular thing, I'll be happy to even send you custom pictures and help you with any of your homework problems. As I like to tell people, it is literally my job to make sure that this makes sense to you. So if this doesn't make sense, tell me, and I will do my best to help fix that. Either way, I don't have anything else to say with this, so have a great day.